So what is environmental testing? Well, there are lots of different types of environmental testing. There's temperature, humidity, solar radiation, pressure, salt spray testing, etc. And today we're only going to be focusing on the vibration control testing. So vibration testing allows engineers to validate the reliability of their products through controlled testing. And these vibration tests are going to accelerate the durability validation process by producing an equivalent lifetime of contributions of vibration, but in less time. So in this picture, what we have is, on the left, a field vibration where we're gathering some data on this profile, and then we're going to reproduce that vibration on a shaker table. So the purpose of the environmental dynamic testing is to expose design flaws of a product in controlled conditions. So we want to reduce the chance of field failure in real-life operating conditions. So during a test, if we break a part, we might ask ourselves, did we over-test the part? If we don't break the part, we have to ask ourselves, did we under-test the part? If we're going to use an established standard, such as like a military standard, we have to ask, is this standard relevant to the type of operating condition that my part would actually experience? So we need to question these vibration profiles and question whether or not we're inducing the appropriate amount of vibration. Oftentimes people think of vibration testing in terms of military or maritime or aeronautical or space applications. These are some of the more common, well-known types of vibration testing. We can test to reproduce events like aircraft takeoff and landing, rocket launch, transportation over rough terrain. But vibration testing can be used for every different type of product, including automotive components, small electronics, printed circuit boards, PCs, disk drives, turbine blades, etc. So really, vibration control testing is applicable to a very wide array of fields. So how do we do this vibration control testing? We'll talk about equipment, a little brief introduction to the different test types. So here what we have is a typical vibration control system. So the typical control system consists of a couple of different elements. First, we have the vibration controller. So in this case, I have a PC with Simcenter Test Lab software, and this is used to manage the test and determine the output needed to recreate the desired vibration levels. Then we have an acquisition front end, and this is used for both acquisition and output. So with this, we're going to acquire our data from the control channels and the measurement channels, and also output the control signal to the amplifier and shaker. Oftentimes we have an amplifier, unless our shaker has an integrated amplifier. And what this amplifier does is it will gain the signal from the front end and input that into the shaker. So depending on the size of the shaker or the size of the test item, a high level of voltage or current might be required, and that's where the amplifier comes in. Then we have our shaker, which is typically either an electrodynamic shaker or a hydraulic device that has a moving mass to recreate the vibration levels. There are vertical and horizontal shaker tables, multiple input, multiple output. So depending on your test type, you're going to have to get your appropriate shaker. And then, of course, we have our test article and our transducers, which are typically going to be accelerometers, although sometimes load or force transducers are also used. And we have to ensure that these have the right sensitivity for our application. And oftentimes we're using both control accelerometers. So when we do our closed loop control, we're going to check the levels on that control accelerometer versus our target profile. But we also might be using some measurement accelerometers, which we won't be controlling to, but we'll still be acquiring the data from. So here we have a couple of different test types covering the frequency range. So depending on the frequency range of the test, different methods might be used. So for random testing, we're covering a pretty broadband spectrum of frequency. With sign testing, we are sweeping over a specific frequency sweep. And with shock testing, those impulse type tests are typically also covering a very high range of vibration. By nature, an impulse has a broadband frequency response. Now, these level versus frequency span, this graphic, this is just a rule of thumb. It's not a hard and fast rule. It's just a rule of thumb to orient yourself as far as what frequency ranges you might expect for each type of test. So let's talk a little bit about each one of these tests, starting with sign control. So sign testing is good for applications dominated by sign and harmonic content. And the sign vibration test is going to be expressed as a profile of acceleration versus frequency. And typically these sign tests are going to be performed as a sign sweep. Now, these tests are usually used where the environment is dominated by some sort of sinusoidal content and harmonics. So think of propeller aircrafts and helicopters, or rotational engine components, or turbine blade passage. So these are the types of things that we might consider as sign dominated. Next, we can consider random control. So in random tests, a wide range of frequencies are excited and measured simultaneously. So the majority of the vibration experienced by a test item is going to be broadband spectral content. So we are going to characterize this by using a PSD, a power spectral density, which is going to characterize amplitude versus frequency. And now the last test type that we'll talk about today is going to be shock testing. So this is good for products that are experiencing explosive or collision events. So if you think of things like handling or transportation or surface environments, and in this case, we're not going to be characterizing it with a frequency spectrum, but rather we're going to characterize it with an acceleration versus time waveform, which will be reproduced on the shaker. Now, all of these tests are going to be performed in what's called a closed loop control environment. So the difference between open loop and closed loop control is in both cases, we have a target profile, we have a shaker, we have a front end outputting that signal. But in the open loop control case, there's no feedback into the shaker. We're just purely outputting a signal and measuring what we're getting. In the closed loop control, we're outputting a signal, and then we're going to check that that output is actually matching our profile. And if it's not matching our profile, we'll update that drive signal and then adjust to make sure that our output is matching our desired test profile. So there's a level of feedback in this closed loop control that we're not getting in our open loop control. So closed loop control is great because we can verify that the test structure isn't in any danger of being over-tested, and we can shape the drive spectrum so that the response of the control transducers matches the target, so we can take into account things like resonances or harmonic distortion and things like that. So the basic principle here, again, we have our control system. Our system transfer function is going to be a measure of the output over the input. And when we're thinking of output and input, we're going to think of it in terms of on the test structure or on the shaker. So the shaker is going to have an input of volts, and the output of this system is going to be the G's of response. So depending on the test profile and the structural dynamics of the shaker and the test object, the drive is going to update to make sure that we stay within our profile. So if we have a resonant frequency, we would have to put out less excitation at that resonant frequency, less voltage, versus if we had an anti-resonance where we would need to put out more voltage. So we characterize the system, and then we use the system transfer function to determine how many volts we need to excite at every frequency.